My name is Dave Danboys. I'm the National Sales Manager for PAC International. I've been with PAC for about 5 going on 6 months, so super happy to be here. I know that we try to have these about 6 a year, and so this is going to be my first opportunity to MC this event. So on behalf of PAC and everybody, we certainly appreciate you jumping on and spending some time with us. We're primarily going to be discussing the primary variabilities that affect acoustical performance in steel stud assemblies today. And this is a deal, or this presentation was all put together by Drake Kentz, who I haven't introduced, as our PAC's acoustician. And right before he jumps on, just want to let you know that we have again a Q&A section that you can we'll try to interact as we can. We can go live on these, but we'd prefer at the end to cover all of those questions. But if you do have questions on anything, just go ahead and add it to the Q&A, and we'll pick it up on the back end. So no further ado, Drake, go right ahead.
Thank you. Yep. Thanks, Dave. Like Dave said, my name is Drake. I'm PAC's acoustician. If we haven't met, hi, nice to meet you. Reach out. We'll set up a meeting, get to know you guys and your team. I'm sure many of you are familiar with my predecessor, Mike Raley. Mike Raley has officially passed the torch on to me, which is an honor. And he's off running the world's coolest acoustical lab, or what will be. It's currently being built. So yeah, anyway, that takes us to this presentation: managing steel stud variables and improving acoustical recommendations. A little bit of a mouthful. If you guys have tuned into some of the PAC webinars before, Mike Raley and in a team effort with Ben Schaefer from Pabco, I've given a couple different webinars on some topics touching on this. This is not quite a rerun, but an amalgamation of several other things. So you may have seen some of this before, but I made sure to throw in some original content in here as well. So hopefully everybody learns a few things. So yeah, let me just get my screen set up right. Okay. So overview, we're kind of start with some concepts and ideas in the introduction, talk about some steel stud variables, mostly gauge and stud spacing. So that'll be a big chunk of this webinar, and there's a lot to be said there. We're going to go over plenty of acoustical data. I'm the acoustician, so I would be remiss to not come with tons of data. And I'm going to show so much data that I don't have time to probably look at every single number in all these slides. So feel free to reach out afterward if you want to dive deeper. I can certainly help there. And then ultimately the goal is reducing variability. So those variables like stud gauge and spacing, how do we reduce the variability of what we see built in the real world? We're going to go over special cases, or really kind of just one special case that tends to come up, and kind of go with some conclusions, and then we'll get to all those Q&A questions. Feel free again to throw them in as we go. Dave will answer the easy ones, but if it's acoustics, it will probably wait till the end, and I'll take it from there. Or construction. If you guys have construction questions or fire questions, Mike Gernhardt is on. He's my boss. He runs PAC International. And he's the construction and fire guru. There he is, waving his hand. He knows so much about fire and acoustics and construction, and so feel free to throw in any of those sorts of questions as we go. So, kind of we'll take a step back. Why does all this matter? Why do we need to talk about these things? Well, acoustical recommendations actually need to be constructible. It's kind of an issue in the field. So I give this story quite a bit, so you may have heard it before if you've tuned into some of the old webinars I've done. But I used to be an acoustical consultant, and as a consultant, I had to be kind of overseeing the acoustics side of projects. But I remember there was this specific job where I had a door that needed, like the project requirements were an acoustic rating of STC 45. And then it had a ballistic requirement as well. I think it was UL 752 level 8. that could be wrong. So someone could fact check me, but that's the number that comes to my head, and it was definitely level 8. So I had to balance these two project constraints, and I was the acoustics person. I knew acoustic door ratings. I had a catalog of doors I could go pull from and be like, these are my acoustic doors, but I had no clue about ballistic rating. So I had to study up. I had to freshen up on my ballistic requirements and learn a bit, and ultimately recommend a door that would meet all the project requirements. Then I would, that was kind of my philosophy there. I would take the same job and recommend certain things about steel stud construction, and other jobs, not only this job, but like construction and stud spacing and gauge and all these things, and make all these recommendations really just focusing on the acoustics and not knowing what the other project limitations were. So a lot of times the recommendations I ended up making weren't actually constructible due to other constraints that I was just kind of ignorant towards. And fair enough, everybody's going to be ignorant towards something, and this has definitely come up a number of times. Other acousticians have empathized with this situation, and you just don't know what you don't know. So hopefully we're going to take a chip off of that today and teach you something you don't know, so your recommendations can actually be a little bit more constructible, and you don't run into situations where you're trying to force something into a project that isn't going to work. So introduction, what's what? There's lots of names for all the different parts of steel stud construction, and you'll see these all on plans, and different regions call them different things, and different groups call them different things. And some of these, it took me a long time to realize were the same things. For example, hat channel and furring channel. I didn't quite know the difference for longer than I should have. It took me a while to realize that they were just different names for the same thing. So just kind of a list. This is far from, a comprehensive list, and there's other things in steel stud design that aren't even shown here. But just kind of to give you a scope of, oh, I've heard this called this before and this called this before. That's normal. That's common in the industry. One thing I will point out is resilient channel comes up often. And resilient channel is called RC. You'll also always see it, or not always, often see it called RC channel, which is a little bit of that ATM machine redundancy. And then RC Deluxe and RC1 are both brand names. So that's, Kleenex versus tissue, that sort of a thing. So if you see that on plans, just know some people often, or sometimes they end up on plans as brand names, and that doesn't always get accurately reflected in like the specifications and stuff like that. So we're going to really hone in here on the steel studs, just kind of an overview anatomy of steel studs, and the different parts. There's the web, which is kind of that depth of your steel stud. So when we're talking about like the air cavity space, that's really dependent on your web. The flange is that face of the steel stud, what you actually screw stuff into. The lip is the return on that other side, how far in it goes. And then the gauge or mill thickness that's a big one. And we're going to spend a lot of time talking about gauge and mill thickness. And that's just the actual metal thickness. So if you hear someone talk about thickness of steel studs, they're often talking about the actual material metal thickness, not the depth or web. So something to note there. If you look at it kind of from the other direction, this knockout, most steel studs have a knockout that you can run stuff like conduit and cable through. Also, you can add bracing through these knockouts. And these are the parts of the steel studs that are specified in the AISI standards. And actually, we'll get into more talk about EQ studs shortly, but EQ studs follow a completely different set of AISI standards that I don't know all the ins and outs of all of this, but they don't talk about all these same measurements and dimensions like you would see here with this traditional stud. So let's start with gauge. Where does this term gauge come from? Gauge, the history of gauge, little history lesson here. Gauge came from the days of pulling wires through these, what you kind of see here in my AI image, part in the AI. The copper wire industry used to pull wires through, like hand crank wires through these draw plates. And in doing that, you would make the diameter of the wire smaller. So you'd have a thinner wire and it would elongate the wire. These holes were kind of conical, so they came to a little bit of a point and had like different thickness openings. And so pulling these through, you could actually decrease the thickness of your wire, and this was pretty standard. Back in the day, there was tons of variability in this process. You have variability of the manufacturer of the drop plate. You have consistency of your metal. How refined was the copper that you're pulling through. Drop plates wear out over time, so your gauges kind of increase based on which ones you're using a lot. But gauge generally meant thickness, but it was really referencing this process. So when you hear gauge, that's kind of where it came from. But an important thing to note about that is this process looked very different for different types of metal and different applications. So thinning a copper wire is very different to thinning like a steel stud. And different metals have different malleabilities. And so if you ever look at like gauge thickness, there's not like gauge X equals this thick, and that's a blanket statement across metal types. Like the copper table looks very different from the steel stud steel table versus the aluminum or tin or brass or whatever else it is. It's all very, very, very variable. So here's a more historically accurate draw plate, just for reference. So gauge is kind of this ambiguous thing, right? So if you do a Google search trying to learn more, try to figure out how thick your studs actually are, you'll find some different tables. And so I just kind of pulled two that I've seen and used before. This left one's from the SSMA, Steel Stud Manufacturer Alliance, I think is what that stands for. So the SSMA has this official table. This is probably the most official one out there. But there's lots of other tables out there that are referencing different things and pulling from different things. And you'll find that if you compare these tables, stack them up next to each other, they don't even agree with each other. And that's, again, because gauge is this kind of more ambiguous process than it is a defined measurement. And there's some tolerance allowed within gauging of a wire, of a steel stud in this case. So it's just kind of nuanced, right? It's kind of tricky. Another thing you'll often see is drywall versus structural gauge. So where gauge kind of grew to mean this process of thinning out your metal, eventually it became more meaning of what the application you want to put your stud in. So if you have a drywall stud, meaning non-load bearing, it has to only hold up its own weight, right? Whereas if you have a structural wall, it has to hold up like some allotted portion of the building. It's load bearing. So to successfully span the height that it needs to span, you can use a thinner stud if you're not holding up any weight of the building. If you have a structural stud, you need to be a little thicker, and they're both called 20 gauge in certain circumstances. So it kind of took another step from meaning the process to meaning the application of what you're actually building. And then you'll also see, as you look through all this stuff, traditional versus equivalent studs. And that's a big one that's talked about a lot. I think at this point, most people are aware of it, but if you're not, an equivalent stud is just basically, taking a little bit of a step back, right? Steel stud manufacturers want to make as much money as they can, and they buy their steel by the pound. So if you are making studs and you can span taller and taller with using thinner and thinner studs, then you have more material bought at that same rate to make more studs, and you can sell more of them. So there's an incentive for these steel stud manufacturers to make thinner studs that are able to perform as well as the old thicker studs used to. And that's called equivalent gauge studs. And the way they do this is by, adding certain folds and certain other geometry, techniques to your actual steel stud design that make them stronger in their vertical axis so they can hold more weight without crumpling. But an important thing to note about that is that as you do that, you get a thinner and thinner stud. You sacrifice other things like your screw pull out strengths. So there's kind of this interplay. But so anyway, that's kind of what traditional versus equivalent is. They also use stuff like strength of your steel. Like there's a lot of material property things that go into it that I don't know all the ins and outs of all of that stuff, but I'm sure you could talk to someone on one of these listed manufacturers here, and they could tell you a lot more. And another thing to note, if all of this isn't enough, manufacturers are changing their studs, and they don't always change the names. So this Pro Stud 20 that's kind of highlighted here by Clark Dietrich, it was originally named that because it was 20 mils, right? So it came out Pro Stud 20 mil thickness, easy to remember. Eventually, they thinned it down to 19 mil using some of these techniques. And actually, now if you go look it up today, it's 18 mil. So it's changed 2 mil, which a mil is a thousandth of an inch. It seems insignificant, but it actually does make a difference acoustically. So lots to know and digest there, and I'm sure we could talk about that for a whole hour if we wanted to. But why does it matter for acoustics? Well, gauge, or like the thickness of the stud, really affects the acoustical performance. So kind of just rule of thumb in the industry is the thinner the gauge, the less stiff your wall is, the less acoustic energy gets transmitted through, the better your acoustical rating is. So we did a sampling of tests here and found that to generally be true. That was generally the case. There's some exceptions, and some of that has to do with lab variability and, certain things like that. But generally the trend, and especially if you go kind of conglomerate a lot of other data that's out there online and stuff, you'll find that trend to generally be true. So let's walk through an interesting example here. And again, I have to shout out Ben Schaefer at PABCO. He did a lot of this testing and has given us his blessing and permission to present it. In the past, Ben Schaefer and Mike Rayleigh have presented it together. And so huge shout out to him. Can't thank him enough. But we tested, many studs. And if we start by looking at our steel stud walls, if we start this by looking at our single layer of type X gypsum board directly attached to both sides of the wall, we can look at the spread. So our best, as we could have maybe predicted, acoustical performance was the 15 mil. That's the thinnest steel stud. And the worst one was the 54 mil. So even though there's thicker studs to the left of that on this graph, this one happened to perform the worst. And there's always just a little bit of nuance and variability with acoustical testing. But that's a 9-point difference. So stud gauge clearly made a huge difference. 9 points is significant. If you repeat that examination, and now we're adding the resilient channel. So this is RC Deluxe, which is Clark Dietrich resilient channel, kind of known to be the best acoustical performing resilient channel. So that's the RC that was used in here. You are now detaching one layer of gypsum board from one side of the studs, and looking at the spread actually shrinks to 4 points. So direct attached, you have a 9-point spread. One layer attached to a resilient channel, you have a 4-point spread, which you might know is important in this exact circumstance. If you have like multifamily buildings and you're trying to specify your studs and your acoustical performance of your walls, this difference here goes from STC 51 to STC 47. That's meeting versus not meeting your code. So just a change in your stud gauge can in this case meet or not meet code. So we can repeat that, and this is now 16-inch on center studs rather than 24-inch on center. And you'll find this time actually the 20 mil happened to perform best instead of the 15 mil, but similar idea here, direct attached with one layer on either side, 5-point spread. And then if you isolate one on the resilient channel, one layer on the resilient channel, you have a 5-point spread still. So yeah, just kind of interesting comparison here. We'll get more into the stud spacing variables in a bit here. But another thing to note is that changing from 24-inch to 16-inch, all these bars drop together. So yeah, that's kind of what acousticians know, or lots of them know all of this. And so the hopeful acoustician might say, let's put these 18 mil thin steel studs everywhere. I've been guilty of this when I was an acoustician. I was like, great, like thin gauge is good for acoustics. Let's take advantage of that. that's actually a cost decrease for a project. So I'm going to be the hero and say, hey, we can use these thin studs that are cheaper and better for acoustics. It feels nice to be the hero because often the acoustician is increasing costs with, like, you know, fiberglass panels and your high NRC ceiling tiles and all the other things that acousticians love to specify. So the hopeful acoustician's like, great, let's take advantage of these studs. Let's space them at 24 inches on center. Let's put 18, 15 mil everywhere. And often you'll find that that is not actually as effective as you would hope. And it's not because the steel studs aren't effective. It's because you actually can't put them in a lot of places. So this is, again, the SSMA table. This is a wall limiting height table. And if you read note 4 here, this is the composite limiting height, which is just referencing a steel stud with a single layer of gypsum on both sides, installed in the vertical orientation. And if you run through this little example, 5 pounds per square foot, just reading the table, L over 240, 3 5/8 web, that's the depth of your stud, and 18 mil, 24 inches on center, you get a limiting height of 13 foot 2. Okay, so great. If I have an 18 mil stud, I can build it 13 foot 2 high. That's, you know, pretty good. And also, I will note in this composite height table, right, you have the stud going vertically and you have a layer of gypsum board on both sides of your stud. That's keeping your stud from twisting. It's acting a little bit like a shear panel. The analogy I often make, which as I didn't come up with this, it's been told to me, but the strength axis of a stud is the vertical axis. And kind of like an aluminum can, right? If you try to squeeze like a pop can with your hands and you're just pushing vertically, it's really hard to squeeze it. But if you give it just a little turn, it just collapses. The same thing can kind of happen with your steel studs. So if you have it vertically in its strength axis and it's kind of constrained from twisting by the gypsum board, it can span pretty far. But if, and we'll see here in a second, if you detach one layer of gypsum board, which we often do for acoustics, right, by adding resilient channel or clips or other things for similar reasons, now you have one side that is not as braced as the other side. So they have another table in the SSMA for braced on 40 inches on center, and your limiting height in that same example drops to 9 foot 3. So not very tall. I think a lot of schools require a minimum of 9 foot, so you're kind of like just passing that. But also, if you're hanging or detaching one side of your gypsum board, then often you're not allowed to hang things from that side. And schools have lockers often on one side or wall-mounted TVs on one side, like the hall side. And then on the other side, they have, you know, cabinets or whiteboards, or chalkboards, and lots of wall-hung things in schools. So you're barely passing that requirement. They probably, like an architect, would rather be closer to the 11, 12, 13 foot range. But you're also adding in this other limitation of not being able to attach things to the wall. So you barely pass a height requirement for schools. Again, other places that requirement might not be applicable. Like they wouldn't allow a 9 foot wall regardless. And you're kind of adding other project limitations in. So those are the sorts of things that, but definitely when I was an acoustician, I was less aware of, and I was like, yeah, let's use these thin studs. And it turns out it's really tricky to even get a thin steel stud to work. And just kind of drive the point home, here's another example of a limitation. If you have low-bearing steel studs and you have multiple floors in your building, you have studs at the bottom are holding a lot more weight than the studs at the top. So as your floors go up, your size goes down. So those arrows are maybe a little confusing, but the thickness of your studs can go down as you get to higher and higher floors. So if you put one wall type together as an acoustician and recommend it, you have other things in the project that are controlling what size studs can go where. So again, a snip from the SSMA. Here's how to read that string of numbers and letters that we just saw on the other slide, excuse me. So feel free to look at that for a little bit if you want. The important one that I want to kind of talk about here is that last number referencing the mill thickness. And an important note is that it's it's specified as a minimum thickness. So you can use thicker studs and still meet the requirements of this like stud specification. And that's also true in the fire designs. So here's a snip from just a random UL design. And if you look at the steel studs, minimum 25 MSG, that's the gauge, steel studs spaced at a maximum of 24 inches on center. So studs are specified, stud thicknesses, are specified as minimums, but the stud spacing are specified as maximums, and that's both for structural and for fire. So even if you get, you're an acoustician and you're pushing for a thin steel stud, a light gauge steel stud to be on a project, if you even can get it, right, there's other limitations that often mean you can't. Even if you can, it's still specified as a minimum. And a builder could just make things easy for themselves and build everything a little thicker. And that happens. I've heard of it and seen it on projects. That definitely does happen. And they don't have to talk to the acoustician. You don't get an RFI or you don't even get informed that it's happening. They're just like, oh, this thicker stud will meet all the requirements. I'll use that. And the acoustician has no clue that that's happening. So another place you can run into some trouble. So you might ask, what about my non-load bearing studs that are not very high walls? Can I use my thin steel studs there? And here's just a sample spec of steel stud. And you'll see just a typical steel stud. They use a baseline thickness of 33 mils. So if you're an acoustician pushing for lighter studs, this is where you need to update things. And it's really hard to get them to actually update things. And it's definitely taking a step away from the standards that a lot of people use. And you'll note that if you're supporting anything beyond the wall itself, the thickness increases. So here is 33 to 54. That can be stuff like porcelain tiles, like if you want tiles on your wall or stones or whatever it might be. Also, another thing to note is AV back boxes and control panels often require the same 54 mil studs. So think like if you're designing a conference room and you want to put the control panel that controls the TV and the microphone and turns on Teams and all those things, that often gets mounted into the wall, and that can require a 54 mil stud as well. So hopefully I've driven this point home enough. The light gauge steel studs are really difficult to actually get on a project. I remember when I was an acoustician recommending these things, I would mark up drawings and say like, hey, can we make these thinner steel studs? And then I'd talk to the architect, and he's like, oh, you want them thinner? I've never heard of that, because most people want thicker and thicker studs. And I was like, yeah, it's going to save you money. This will be great, and it'll be better for acoustics. And then the next set of drawings come back, and it's thinner studs, the same studs. They didn't get thinner. And I'm like, hey, what the heck? Can we please get these thin studs on the project? And even if you do successfully go through that rigmarole, you'll end up in a place where they're specified as minimums. And other project constraints often drive that thickness up. So the other thing we use often as acousticians is stud spacing. Kind of the general rule and thought is that 24 inches on center, that's less area for your studs to contact your gypsum board, and overall less stiff walls. So that would be better than 16 inches on center acoustically. So kind of to drive that or illustrate that point, the red space here is where your stud would contact your gypsum board. If you reduce to 16 inches on center, you have a lot more red space, right? So that's more area for acoustic energy to be transmitted through. Overall, more radiated energy comes out the other side of the wall. So earlier we saw the stud spacing did affect the resilient channel as well. And so we'll kind of go through that same exercise here with the resilient channel. This is a sample wall with the studs at 24 inches on center again, and resilient channel on 24 inches on center. And if you count all the little crosses where everything passes through each other, and for reference, everywhere that the resilient channel crosses a stud, it has to get screwed in and attached. So you have overall 35 contact points between your resilient channel and your studs. If you decrease your spacing of your studs to 16 inches on center, you increase your contact points up to 50. and that's a 43% increase in number of contact points. So, excuse me. So more points for the acoustic energy to get transmitted, and so worse overall acoustical performance. So let's repeat that now with clips on one side. So the clips can be attached at 24 by 48 in this kind of alternating grid pattern, and that's not as dependent on your stud spacing. So if we go through that same exercise, here's 24 inches on center studs, decreased to 16 inches on center studs, you actually only added one contact point. So that's a 5% increase. So if the theory holds, it would be a lot less of a difference, right? Using the clips. Okay, so let's go beyond theory and single numbers and dive right into maybe the hardest graph to digest that I've ever seen. And here I have to shout out Ben yet again. He put this together. This is a lot of his test data, and it's a lot to look at and a lot to think about. So I'm going to walk you all through it. Don't worry, we're diving in it together. But if you look at this graph, on the bottom axis, we have frequency. So low frequency at the left, high frequency at the right. Then if you look at this vertical axis, we're stepping down in our stud thickness, or stepping up in gauge, right? So our thin gauge studs are at the top, and our thick structural studs are toward the bottom. And then the color code represents the difference in a 24-inch on center spaced wall versus a 16-inch on center spaced wall. So what we're doing is we've tested a wall type with 24 inches on center construction, and then we've retested it built at 16 inches on center and found the delta. And so as we look at it, you know, the Roy G. Biv, the rainbow, if you're at the Roy part of Roy G. Biv, that means 24 inches on center outperformed 16 inch on center. If you're at like the Biv part of that, you're at, that means that the 16 inch on center outperformed the 24 inch on center. So hopefully that makes sense. Feel free to take a snip of this or ask me to show you it later, and we can scratch our heads about it together and a lot longer than we can here. But generally what we find is that comparing 24 inch on center to 16 inch on center, most of your difference where 24 is actually better than 16 is at the 125 to 160 hertz region. If we repeat this now with 2 layers of type X chip on both sides, you can see the same effect, just kind of exaggerated. So some more of that red right at 125, a little less here at 160, but still present. And actually, you'll note below that range, 16 inch on center was better than 24 inch on center, which is kind of counter to what we tend to think. So kind of another complicated graph, but what we're doing is we're basically splitting away. That the previous graph was looking at the deltas. Excuse me. This graph is looking at both next to each other. So 16 inch on center at the left, 24 inches on center at the right. And when it comes to that low frequency, what is actually happening is we're decreasing the resonance of the stiffness of the wall. So if you're not aware, the STC curve starts at 125. And you can see, if I go back a slide, that's where a lot of the differences are. And often a wall will get 8 dB limited at 125. So if you shift your resonance below 125 in frequency, you improve the performance at 125 by quite a bit. And if you're 8 dB limited there, you can have a significant difference in your STC rating just by changing your stud spacing. But what you're not doing is changing the actual amount of acoustic energy that's getting transmitted through this panel. Or maybe you are a little bit, but you're shifting a resonance lower, and it's just mostly being ignored by your STC rating, which is kind of one of those problems when we want to use a single number rating for everything. We lose a lot of resolution and clarity on some of the more nuanced things that are happening. So if you have a wall where you're worried about things below the speech frequencies and below STC curves, and you have some low frequency energy, and you say, let's use a 24 inch on center spaced wall because that's better for acoustics, that might not actually be the case. You might actually make your problem worse. So kind of some of these rules of thumbs can fall apart when you start looking at things a little closer. And so let's repeat that now and go back to detaching one side of gypsum board again on RC Deluxe. And you'll see that a lot of those differences, both in terms of, so it's consistent across this vertical axis for the most part, right? And this is again looking at deltas. A lot of the deltas shrunk. So what that means is your dependence on both stud spacing and mill thickness shrinks as you detach things from the wall, or detach your gypsum board from the studs. So we wanted to go ahead and test two of our different isolators that do this, that they detach gypsum board from the wall, decouplers, right? We have our Rizik V on the left, which is just the metal claw part of our Rizik 1, which hopefully you all know and love and specify all the time, right? The Rizik 1 is just a metal claw that holds your hat channel or furring channel, whatever you want to call it, and has a rubber bushing that attaches to the metal studs. The Rizik V just removes the Rizik, or the rubber channel. So you have some metal to metal contact, but you also have the weight of your gypsum board pushing down on this friction fit claw, which provides a little bit of spring action. So it works, I would say, surprisingly well. And we're going to go through a bunch of data. We tested these two isolators on 33 mil and 54 mil studs, just kind of to get a good representation of the minimum of what can actually be built based on all that stuff we looked at the front end of this presentation. And then 54 mil is more of the structural increased stiffness studs. Okay, so 33 mil steel studs at 24 inches on center. We can see that comparing these different attachment methods from bottom to top, we go from direct attached. Above that, we have RC Deluxe. Above that, we have the Rizik V. And above that, we have the Rizik 1, right? So we see a huge difference here at the coincidence dip. Clearly adding these isolators, adding these decouplers makes a significant difference there. At the low frequency, we see relatively good agreement. If you look close, it kind of looks like the kind of peaks of these different, if you can see my mouse, some of these peaks shift about a third of an octave band from changing like some stiffness resonances and stuff like that. But relatively good agreement at the bottom. So then let's change now to looking at 16 inches on center. And you can see the same improvements here at the coincidence dip, but down lower frequency, you actually see much more of a spread, whereas before they were much more tightly clustered. And then kind of here down at the bottom, they tend to converge, and you actually have a trade-off where some of the resonance, again, right, a lot of this low frequency resonance controlled stuff, you're shifting resonances down, so the methods actually kind of flip a little bit, but not too much, just kind of some interesting data to look at. So repeat on 54 mil studs at 24 inches on center. We see a very similar thing to what we saw with the 33 mil on 24, where we have, again, big differences up here at the coincidence dip, and much better clustering here at the lower frequencies. And now again, moving to 16 inches on center, same dip here, same stacking, but then this spread is back, right? The big changes at the low frequency are back, with kind of things converging down as you go lower and lower. So let's flip this, right? We've been kind of looking at the different attachment methods and iterating between the different gauges and spacing. Let's control for the attachment method and look at one plot with all the different spacings and stud thicknesses. So this is direct attached, and you can kind of see there's quite a bit of spread here, huge spread down at the low frequencies. What is that, like 10 plus dB differences between the stud gauges and stud spacings? So this is very consistent with what we've seen this whole time, especially when you've directly attached your gypsum board. Your performance of your wall is very dependent on stud spacing and stud gauge. So we add our decoupler the RC Deluxe here. And you can see there's much better clustering, right? Things are kind of converging, coming closer together. But there's still some broadband variability. And then down here, there's still some of that low frequency spread, especially with the stiffest and most or least spaced studs, 54 mil at 16 inches on center. Stepping up again, all the lines kind of go up a step. This is the RISC V. The clustering's getting better. Things are kind of converging. A lot of these differences are starting to fall within your lab variability. So you have to kind of take any deltas here with more of a grain of salt than before. You kind of still see some spreading down here, but it's reducing. And then the RISC 1 is another step up. And there's still some differences at the higher frequencies and coincidence dip. But for the most part, things are clustering pretty well. So if we kind of condense that back into these single number ratings that, take single number ratings with a grain of salt. But you can see this chart, 33 mil, 54 mil, 16 inch on center, 24 inch on center. It's all within a point, right? Which is pretty much negligible. It's definitely not noticeable to the human ear, this 1 point difference. So decoupling tends to reduce your reliance on both stud spacing and stud gauge. So special cases, let's talk about double studs. Double studs come up quite a bit. They tend to be, walls that require a high level of acoustic isolation, but because of the nature of where they're getting installed, they also tend to have very tall walls, right? So you have these really tall walls that need to be providing a high level of acoustical isolation. So if you have that, the question inevitably comes up about, what about bracing? If you have these tall walls, they need to be structurally sound, right? If we remember back to the limiting height tables, having a layer of gypsum board on both sides of the studs was very good for acoustics. So in a double stud, you by definition don't have that on the inner layers of both of your studs. I guess you can, but that hurts your acoustical performance. So you need to brace them. And people are very concerned about tying your studs together because that's an acoustical short circuit. So if you actually go look at the UL requirement for most of the double studs, I went and searched through a handful of them and found this was pretty typical. They reference the SSMA for bracing. And then if you go look at the SSMA's bracing details, you see these three details here. They're all laterally braced. None of them are tying your two studs together. So you can do these three methods. Some of the other ones allowed for like cross bracing, which is where you kind of make like a big X on your studs. So you tie like your wall section corners together, which is another form of bracing, but it's all on one side, right? None of this is tying your two studs together. But it can and does happen. I'm not too familiar with every situation when you would, but I think it would be if it's like not fire rated and there was some like seismic reason to, or like wind load or something like that, right? So it does happen. So we went ahead and tested your double stud wall, unbraced versus braced. And just like we kind of suspected, bracing really hurts your acoustical performance. Also, I'll note this isn't only an acoustical short circuit, it's also a thermal short circuit, which is I think why the UL design doesn't typically allow for this type of bracing. So just another thing to note in all of this. But point being, when you brace it, when you tie these two isolated tracks together, you lose a lot of your acoustical performance. But if you add the same decoupler, right, this is our RISC 1 to one side of it, so you're, instead of having two isolated stud tracks, you have two tied together stud tracks and an isolated layer of gypsum board, or in this case, 3-layer based on the wall we were building. But you're isolating the panel rather than the two stud tracks. You gain a lot of your acoustical performance back. And you can see there's only a 3-point difference here between fully unbraced and the RISC 1, which is pretty good. And, with this kind of big beefy wall, I would expect some variability to be kind of increased beyond what we normally see, but so variability could be part of it, but there might still be some acoustical sacrifice. But then that kind of begs the question, if we can see isolating just the panel of a double stud, basically provide similar to maybe equivalent performance, like isolating the panel versus isolating the two stud tracks, can we see a single stud wall perform at the level of a double stud wall? while minimizing our thickness as much as possible. So as we all know, double stud walls tend to perform better than single stud walls. And here's just a comparison between the two. And these use the same web, right? That was the term from back at the beginning, the same depth of stud. And if you put them on a graph, you'll see kind of the difference you would expect. There's some agreement here at the middle, but up at the high frequency and low frequency, there's certainly some differences. So if you go look at, again, some steel studs, double stud walls, kind of changing the spacing and the gauge of the stud, you'll find that much like we found that decoupling the gypsum board removed your reliance on stud gauge and thickness, spacing and thickness, so does using a double stud wall, right? Which is kind of in line with what we've been finding. If you're isolating these two things from each other and you have this big open cavity, then your reliance on spacing and thickness is not as dramatic as it was. So maybe a little bit at the low frequency, you still do have some reliance, and there's some deltas, but for the most part, we find that that's pretty true. So instead, let's control the total airspace. We saw a 5-point difference previously, comparing the same depth studs of a single track versus a double track. If you control the airspace and let the double stud wall have thinner steel studs, you find actually there is a lot of agreement between isolating just that layer of gypsum board versus isolating both stud tracks. And of course, with acoustics, everything's got a little asterisk. So if you jump into the third octave band data, you'll find some differences, but for the most part, pretty well in line. So I think I'm running low on time here, so I got to my conclusion slide, which is good. But I guess my big takeaway from all of this is, what would I do different as an acoustical consultant if I was consulting again today? I think I would not be specifying stud gauge and stud spacing nearly as much. And I've talked to other acousticians who have made 33 mil just kind of their generic wall type for all of their steel stud wall recommendations, knowing that you're not going to get anything much thinner than that through a design. So using other methods, especially decoupling, can reduce your reliance on those two properties of your studs and your steel stud construction walls. In decoupling, there's still a good, better, best. We kind of saw that with the RC Deluxe to RISC V to RISC 1. But there's other layers of improving acoustics that have their own pros and cons. Constrained layer damping, I have to shout out Ben Schaefer at PABCO one more time. Couldn't have done this without all of the data that he has so generously let us present and tested with us back before I was here. And also, always, you can add more and more mass and improve your acoustics. Okay, well, that kind of brings us to questions. Dave, have you been watching the Q&A? Do we have a list?
Hey, Drake, hey everyone, this is Mike from PAC here. I wanted to step in and add a few notes that I don't even know if Drake was aware of. One of the things, Ben did great work. He did this huge series of tests. We were able to piggyback on the back and add the PAC stuff to that. So again, thanks a lot to PAC or Ben and PABCO over there. A couple test notes, and there's some people in here that I want to ask this question to. The reason we tested, and it's the Dietrich group, Jose and a couple other people here. I'd like to get some clarity on, or give some clarity on why we tested with RC Deluxe. We tested with RC Deluxe because to our knowledge, it's the only resilient channel that actually has a true steel spec for it. Like, it's a very specific type of steel, whereas all the other RC channels, for lack of a better description, use generic 25 gauge or stiffer steel. And the reason we use RC Deluxe, again, is because it is the most tested. It's been around, it's been out since the 60s, the design of it. So we can turn the mics on here. If the guys from Dietrich want to step in there and either validate or change that part of that conversation, I'd love to hear your input on that. If you want to put your hand up, I can turn your mics on. The other thing, and I'll just run through these and then we can get back to the RC Deluxe. On those higher performing steel studs walls that you saw, those were cross braced because they were planned to be over 30 feet tall. That's why they had so many layers of gypsum board on them. We saw the steel studs were 8-inch steel studs at, I think, 14 14 gauge or an equivalent to that. Or I'm sorry, 12 gauge. So very stiff, tall walls, and we had to use that size steel to get to that 30-foot height, which is kind of where this conversation started of like, well, how does mill thickness actually affect these wall performances? And then the double stud walls, you were 99% right, Drake. I've seen, because I'm the construction guy, I've seen on plenty of jobs where if it's a double stud wall, even an 1 5/8 steel stud wall, they'll just scab in a piece of drywall on 1/3 intervals moving up the wall because it's stuff they have laying around, or they use a piece of steel stud or track to create that cross bracing. Mostly because it's cheaper than the alternatives, which is spacer or U-channel and L brackets, or putting exterior bracing on there. So if the group from Dietrich is here, if you want to have some input, I'm more than happy to let you guys make that correction if I was incorrect.
Jose,
I think we have.
are you able to allow Mike? There we go.
You got him.
Jose,
Okay.
you should be able to unmute.
All right, thank you, Drake, for the presentation and the information.
You bet.
And Mike, thank you for the note. I do agree. And Clark Dietrich Resilient Channel, like you said, is the most tested resilient channel. So that is true. If you follow the path of the channel itself, it goes back to the Unimast company, which was acquired by Dietrich, and by nature coming back with the merger with Clark Dietrich. So the profile and the systems have not changed in quite some time. And that's not to say that the tests from 40 years ago are exactly the same as it is today, right? Like, as we all know in the industry, wallboard has changed, insulation has changed, even screws have changed, right? Like the screws that we used to use 40 years ago are not the same to the same manufacturing tolerances, right? Like, because the science has advanced so much. So and the bracing options, that's definitely I agree with that. There's a lot of variability, but there's a lot of things that have been proven throughout the years that work in similar conjunction. If you look at U490 or U493, is a UL design that allows for all kinds of bracing for those chase walls, right? So even from the fire standpoint and the constructability of the fire standpoint, you could do that. So.
Right, but the lingering question is, do we have an acoustical test that matches those UL designs, right? Which is kind of the intent of this is the acoustical side of that. Totally understand. Correct. Yeah, there's tons of bracing options out there. There's, with science, things get better, obviously, but also the requirements increase too. Structural load requirements, shear values, seismic bracing, all of those things are also changing at the same time. So the science has been forced, as you know, to increase with that, which has created, more better systems, which is fantastic. Okay, great. Yeah, and the reason I wanted to touch on the resilient channels is because we knew that if we ordered RC Deluxe, we would get that specific steel. If we ordered any other resilient channel, those results could have been drastically different. If we would use even RC1 Pro, which is more consistent than a lot of the other manufacturers, it's still made from a different steel. So it doesn't perform as well, just generically speaking, right? In ceilings, it's a couple points lower. I don't know what it does in walls, and that was something we weren't willing to risk on a test series.
I'd like to chime in on that. We actually tested recently, and we have those results on our website. We tested recently a bunch of walls and ceilings, and we found out the Resilient Channel Deluxe outperforms on ceilings, even with the new lightweight boards. So it's still significantly proven that its performance is valid.
And I don't know how many distributors are here, but I'm sure you're aware, I ran a drywall supply yard for 20 years, and I think in 20 years I had maybe 3 lifts of RC Deluxe in my warehouse, and that's just because the customers are cheap. They want the cheapest RC channel they can get. They don't know the difference. So, and at that time, 35 years ago, I was unaware of the difference too. So as I've become more educated, we've been trying to educate the distributors in the same manner to help protect their customers and the architects and the GCs on their projects. So, I appreciate all the work you guys do over there in testing, and it's good to have some partners out there, or competitors, however you want to call it, that that are also doing a bunch of testing and expanding the market, because it's important to bring some knowledge to this market.
Absolutely. Competition makes everybody better.
Yeah, sure does.
All right, I'm reading the Q&A. I see a couple questions, but Dave, I'll let you pioneer or head the Q&A
Okay,
discussion.
yeah. So Joe Morris, he had a question. What are some of the other methods of increasing or maintaining my STC rating for doubling the stud walls that have been braced without adding a resilient channel or clip? Can I space out where the braces are, where the braces are integrated, or see less?
Oh,
Sorry
I
about
see.
that.
Yeah.
Or see
Okay.
less.
So yeah, if you are connecting these two isolated stud tracks, the nice thing about a double stud wall is that you have two stud tracks that are, in theory, not touching as much as possible. Bracing it kind of short circuits the acoustical benefit. So the example we walked through was reintroducing your isolation by decoupling the gypsum board. You can also probably get there just through brute force mass law. Add enough mass to your wall and you'll get there. Also, there's constrained layer damping. So Ben Schaefer with PABCO, they make Quiet Rock, which is you have like a thinner layer of gypsum board and then an inner layer of like a viscoelastic material, and then another layer of thinner gypsum board, and that can improve your acoustical performance. But yeah, other than once you've short circuited it, it's hard to unshort circuit it. You have to.
Yeah. And Joe, your bracing is usually defined by the structural engineer or the fire rating on the wall. So a lot of times you can't reduce or increase spacing, I should say, on those braces.
Cool, thank you. And hopefully I don't mess this name up. Olvera Egger, you mentioned trouble mounting things to RC walls, but are there smaller issues? Are there similar issues with mounting to Rizik walls? Right.
So mounting to your RC walls, there's screw pull out limitations to what you can mount and weight limitations, but also with the Rizik 1 you have to use a light gauge hat channel to mount to. So yes, you do run into issues. We do have, for this specific issue, Rizik 1 backer, which is just kind of a actually here, I'll just show you. I've got one on my desk here. Here's the Rizik 1 backer. It's just like a thicker gauge stud seal that can get mounted to your studs and then comes flush to where your hat channel is, like the face of the hat channel. Yeah, perfect. And we found that it is not a significant compromise acoustically to just your Rizik 1 wall. And then you can mount to that. So it would be not unlike adding blocking to know where you're going to mount things. And, a little bit of planning has to go into that too, though.
Yeah, and that backer can hold anything from cabinets, headboards, floating nightstands in hotels, handicap grab bars, railings, and anything that is going to have either momentary or constant load on it.
We also make a resilient channel backer. So same concept, but for a resilient channel wall. And it's just kind of isolated blocking that you can mount to. So if you run into that issue on either a Rizik 1 wall or an RC wall, we do have some solutions there.
All right, thank you for that. We have one more from Jacob Davis, and he ended the message by saying, I may have misunderstood what you're discussing, but what are some theories on how reducing OC can result in smaller increase in performance in some walls?
Okay, so reducing the spacing of your studs, overall you're shifting your stiffness resonance of your wall lower. And so the big thing is that your STC rating stops at the low end at 125 hertz. Another rule within the STC rating calculation is what's known as the 8 dB rule. So if you're comparing your actual like transmission loss performance to these kind of pre-agreed upon curves of STC ratings, and you find the difference. If you have a curve that kind of looks like this, and you have a performance that kind of goes up and down, one of our rules is no single 1/3 octave band can be more than 8 dB different than that reference curve. So kind of in the weeds. Talk to an acoustical consultant or email me if you need more details there. But this 8 dB rule often limits your performance. So we have several other rules in the calculation, but if you're 8 dB limited, making a change at the 3rd octave band where you are 8 dB limited can make a significant difference to your overall STC rating. And if that happens to be 125, and then you decrease or you increase your stud spacing, you shift your resonance lower, and all of a sudden your performance at 125 improves by quite a bit. And now you're kind of ignoring this resonance spot. It goes below your STC rating, and your STC rating shoots up. So if I understand the question right, that's kind of what you're asking about. It's a little bit of a nuanced concept, but
so for everyone that's here, if you're not familiar, STC is speech. It's aimed at the human voice. So that's why it only goes down to 125 hertz. Now, if you're dealing with an interior exterior wall, maybe a corridor where you have a lot of rolling items, like in a hotel where they roll a lot of things down the hallway, your primary noise may be actually a lower frequency than what the STC is really aimed at. So now you're talking about, and that's where I think we see some performance variances below 125 hertz, where you see some wall types have varying performances, and then up in the STC range, we see larger gaps, right? But down in low frequency, that wall that maybe was an STC 40 versus 45, maybe the 40 at low frequency performs better, because it's an unmeasured area that doesn't apply to the STC rating. So I think for me, that's how I define that. You gotta remember the STC is speech. It's not all noise, right? If you're in an exterior wall and you've got a highway next to you or an airport, obviously you're going to have some 50 hertz, 60 hertz noise. Then you have to really examine the entire wall and all the measurements possible as low as you can, hoping that the labs have enough volume to actually measure it correctly.
And that they report the data that's another limitation to that analysis. So
that looks like that's all the questions that we have. Like Mike had mentioned about 58 minutes ago, that this webinar will be on our site, on our YouTube channel. We truly appreciate everybody's participation in today's webinar. We hope it was a meaningful hour for you.
Mike, I saw you put your hand up. Did you have another thing?
No, I accidentally put my hand up. I was trying to click on something else. But Joe, you had asked if the slides would be available. I think I replied to you in the chat. Email Drake directly. He'll get to those.
Absolutely.
Thanks, everyone. I appreciate it.
Thank you.
Yep. Thanks, everybody.
Take care.